Okay, so you are doing some classical EM theory with polarization of light. You will have some problems set to, there's a question from a student. So I think you will have some homework problem to deal with how polarized, how circularly polarized light will interact with atom. So let's move on. I would like to write down the key answer without derivation and then move on to derive the key result. Because at the end, it is one equation that we need in order to move on to understand the physics of how absorption, emission occurs in an atom. Whether that equation you know how to derive it step by step or not, really doesn't matter. You take that equation and move on, you get all the physics. So at this point, I would like to first write it down in a reasonable way. Namely, at least that looks quite okay. All right, so let me try. I'm improvising actually. So the question is, we have an atom initially in some initial state. Then you have a perturbation terms come in. Usually it depends on time and the position of the charge that kicks in from time equals 0 onwards. The question is, what is the probability? Amplitude, finding the system in a final state at time t. Okay, so that is the question. So we are thinking about something like, this is time equals 0. So this is time. And we want to ask, say, this is time t, all right? Whether this transition could happen. And if we can find this, then this thing will be the probability of finding the atom in the final state, all right? So let's think about a very hand-waving or baby level argument. We only look for something called the first order theory, meaning this thing interact only once, leading to the transition. So we can think about somewhere t prime at which h prime will take the system out from the initial state, and then there is some probability that it is in the final state. So let's think about the following situation. Let's see whether it works. I'm 100% improvising. So let's see. From this point, the system is in the initial state. And then it remains in this initial state say up to t prime. So at that point, it will pick up a phase factor like this. So at least you understand what I've written down up to here. I'm saying that nothing happened from here to there, and something happens at t prime. Okay? Now, from our previous discussion, we know it is h prime that is taking the system from the initial state away, and then some probability in some other states. And that occurs at t prime. So this has the effect. An operator operating on the initial state at t prime will give you some other state. That state will have some chance to be in the final state. What is that chance? We project it into the final state at that time. Okay, so what we are doing is that nothing happened from 0 to t prime. This takes the state away from it, and then this is the probability amplitude of this whole thing being found in the final state. Okay, and then for the projection, we need to do the spatial derivative. It's projecting this whole thing onto the final state. Okay, finally, what we discussed could happen at any time t prime between 0 and t. This t prime is arbitrary. Okay, so therefore, this is a possible expression for what we want to find. Okay, so this will be the key equation to move on. Remember, we have a form for this, which is E R dot field cosine omega t. So it does have an R for you to R prime now, because R, sorry, I don't know how to erase it. Sorry. So it's R. So there's an R for you to integrate over, and there is a t prime for you to integrate over. Okay, and then you have other time factors here and there that has to do with the final energy and the initial energy times t prime over h bar. It started to look at something like there's a condition of this factor that goes like with this that will give you the requirement on the energy. Okay, so this is my hand waving argument of the key result to move on. Okay, now if you are happy about this, take a rest for 20 minutes and then come back, and then we will try to see what is the physics that we can extract from this. So at this point, we will start our formal discussion about time-dependent perturbation theory. Nonetheless, this is the key result to move on. Okay? I don't know how to save it. Let me see. Stop sharing. I'm looking for the separate part on. Okay, do you see the notes on time-dependent perturbation theory? You see that? Okay, now I posted as a separate section, not continuously, because this also form a part of the formal quantum mechanics. So if you want to sort your notes, say this is theory and this is application, this is the theory part. So let's start. Let me flash you at the end what we have. This is what I want to get at. This is what I just wrote down for you. All right. So let's define the problem. More formally, we have a H0, which is our atom part. More importantly, it is time independent. You solve the atom part, which I now call H0. You solve this time independent Schrödinger equation. These are atomic states. These are atomic energy levels. So you know all of them. We also motivated that we need to play with a time-dependent perturbation. We have a specific form in mind, but for this section, we don't need this specific form until the end. I don't want to carry the R in H prime because I would like to emphasize the time dependence, which is the new element here, but you should remember that it is both spatial and temporal dependence. It is an initial value problem. So before time equals 0, you have H0 only. You know how to solve that. Now time equals 0 onwards, this part comes in. The question is, what is the probability of, say, initially it is in some state, phi n or phi I initial, what is the probability of finding it in some other state, phi m or phi final, after the perturbation term comes in? So let's motivate the procedure. I would like to remind you the following. This is also this week's sample question 18. So you can also go to the exercise class to consolidate what we discussed here today. If the perturbation term is not there, you only have H0, that is easy problem. And then let's say you already solved the problem. I lost my mouse. Okay. So this is the Schrödinger problem. And now, if you are given initial state at time equals 0, which is a linear combination of this energy eigenstate, you can write it in a shorthand notation like this. Let's say it is given, initial value problem, given that, so these are known. What is the wave function at time t? You use time dependent Schrodinger equation, you get that every factor will evolve with its own phase factor given by such a phase. Okay, so this is the time-dependent wave function. Given initial wave function, what is the wave function at a later time? We know how to solve it once we solve this time-independent Schrodinger equation. So for our purpose, the most important thing to note is the following. At time equals 0, you know this. At time equals t, these are the same coefficients, meaning the coefficients an are constant coefficients when you have h0 only. They are time independent when you have h0 only. Now, our question is, we have a time dependent part, h prime of t. First thing first, this is no longer the case because we have an additional part. What you did here, this thing, are not eigenstate of h. So you cannot simply use this phase factor. Then Dirac proposed the following approach. What we are going to do downward is called the Dirac formalism. And later on, also credit was also given to Fermi. There's something called the Fermi golden rule at the end. But this starting point argument was due to Dirac. So Dirac was very clever. He said, let's write the following thing. Let's put some time dependence into these coefficients. H0 only, time independent. All the time evolution of H0 is taken care by this factor. So he was thinking, how about this? We make this coefficient time dependence. What is the physics? The physics is H0's time evolution is taken care by this. And this is time independent. Therefore, all the effects due to h prime of t, the time dependent perturbation, can be put into this time dependent coefficients. So basically, it is swapping unknown, right? I put all the unknowns into this many coefficients. First of all, you must notice there's no approximation here. Equation A4 is simply suggesting a way to move forward. Let's write the solution at time t to be in this form. Therefore, it depends on whether we can solve for this time-dependent coefficients. But we know if h prime is not there, it will not be time-dependent. It will be a constant. That will be the zeroth order solution. Therefore, we will look for dynamical equations, meaning we want to find the equation governing the time dependence of these coefficients. Okay. So we have, at least, we have found a way to move forward. The question now becomes, I have this Hamiltonian problem. the solution is in this general form, can we put them together and use the time-dependent Schrodinger equation to derive how these coefficients depend on time? If we can do it, then we are done. We take A final at time t, make a square, that is the probability of finding the system at the final state. Okay, so let's move on. We only have one governing equation, which is h phi equals I h bar d phi dt. That is the time-dependent Schrodinger equation. For our problem, it is a time-independent part. We know all the solutions, plus a time-dependent perturbation part that we want to know the effect of H on making transitions. So this is our governing equation. So we have left-hand side and right-hand side. Okay, so let's work on it. Next step. Take this proposed form, plug it into left-hand side, plug it into right-hand side, equate both sides, and see whether we can look for dAnt dt, the dynamical equation governing the time evolution of the coefficients. So do you understand the idea? So next, let's move on. Left-hand side. Two terms. This operate on time-dependent part of the coefficient, okay? And then we have this evolution due to h0 embedded there. So first term, h0, we'll look for spatial wave function to operate, okay? So, but these are energy eigenstate. So h0 phi n will be En phi n, you see? So the first term is simple. Second term, we have the perturbation, okay, operate on each component. We can do nothing, just leave it there. So the left-hand side, two terms, all right? Right-hand side, do time derivatives. The time is hidden in two things, time-dependent coefficients, and then up there, exponential time there. So when you do d phi dt, there are two terms. First, do this, you will bring down the prefactor. That is first term. Second term, you start to get what we want to do. The dynamical equation, how each coefficient evolves in time. I use a simple differentiation here because this coefficient depends only on time. It's not partial, so it's simple d dt, all right? So we have left-hand side, two terms, right-hand side, two terms, okay? But the lovely thing is that one term on the left-hand side is exactly the same as one term on right-hand side. Cancel them off. The equation becomes this, equal that. Okay? It's still exact, no approximation, step by step. Therefore, the time-dependent Schrodinger equation is now rewritten as, I'm using this, I'm writing this on the left now because I want to get this, okay? Equals one term there, okay? So far so good, right? So this is still equivalent 等价的等价的 to the time-dependent Schrodinger equation. No approximation. This is exact. But what follows, I would like to simplify notations. Well, some of you may think I'm complicating the notations depending on your taste. I would like to focus on only two states. So I'm thinking about something like a two-level system. But for every equation to follow, it is very easy to immediately write down all terms when you have a summation over n instead of only two terms. So more specifically, I would like to focus on two states only and call it 1 and 2. Their energies are called E1, E2. So instead of summing over n equals 1, 2, 3, 4, 5 to a million, I would like to focus on two terms. So rewriting A6, it means the following, just to be explicit. There are two terms here only. So I have a dA1 dt, and then I have a dA2 dt. These are the things that we want to solve. Okay. On the right-hand side, I only pick up two terms. We assume only two terms only. So I have a A1t, I have a A2t term. So this equation is A6 written down for a two-level system only. Okay? I hope that you know that it is only one equation we are playing with, not many. But later on, from this equation, we will project out a set of two equations. Okay? So do you follow me up to here? Any question? Small question. It's the small question. There's the students they're telling me. Okay. So let me move on until I see your question typed it. So now we have all the ingredients. We want to single out. The question was, are we preparing to use variational method? The answer is no, we are using perturbation. Okay. So now the next step, before we do any perturbation idea, is still exact up to here, is to find an equation for this thing alone. And find an equation especially for this thing alone. Because if we assume initially it's a state 1, it is A2t that we are interested in. So let's consider how we can have an equation dA2 dt alone. Okay? We know this energy eigenstates are orthogonal to each other, right? Therefore, if we want to project this thing out standalone, you times the phi2 star here and do a spatial integral, you can kill one term by orthogonal arguments. Okay? So you understand that. This is exactly what I write down here. Understand? You do this, you kill this term by orthogonal, you keep this term, you have this thing integrate for itself, is normalized. So this is the left-hand side. Right-hand side, let's look at it, sorry. You will have phi2 star here. Remember, this thing is actually RT. So you have a phi2 star, H prime R, and phi1 R to integrate over. Okay. Similarly, for the second term, you have phi 2 star h prime of r phi 2 r to integrate over. And that is what I wrote down on the right-hand side. Okay. So there is r here, and I was just lazy, haven't put it down here. Okay. So we succeeded in single out the A2 dt. So if we want to get a dynamical equation, dA2 dt alone, we can multiply this to the right-hand side, this side, okay? So that goes to the other side, becomes plus E2, right? So finally, you have this, A1T here. This phase factor comes from multiplying this term to the other side. That is good. You start to pick up the difference in energy in the atom. And then you have a spatial derivative that has to do with initial state 1, final state 2, and the perturbation in between. Bravo. We know the physics, right? H prime is responsible for bringing in transitions. So we have this very physically explicit in our integral here. Second term, similarly, we have A2 here, okay? And this term multiplied to the right-hand side times this become 1. So you don't have a phase factor. You have this same state and then the perturbation. In many problems, let me announce this is 0 by symmetry. But generally, we are doing the formalism here. We will keep this term at the moment because maybe in some other occasions, not thinking about atomic transitions, this is still general. Okay, so done. This is A2 time evolution equation. Do you think you can write down the equation if we keep the summation n? You see the pattern of the terms, I hope, right? So if you have a term number 3, A3, the level, the third level, I think you can easily include another term into the equation. Now, you go back to the general equation. If you want to single out this, you do the same. You multiply phi 1 star, do the thing. You get this equation. Okay? So, let me summarize. Up to here, these two equations are exact. Well, besides I single out two terms, okay? It's exact, meaning we haven't made any approximation yet. We have rewritten the time-dependent Schrodinger equation in a more manageable form, okay? Second, it is coupled, well, formally, So it is coupled in the sense that when I look for the dynamical evolution, time evolution of A2, it has to do with A1 and A2. Similarly, this dynamical equation, I have A1, A2. So you can think about if you have the third level, there's a A3T and another term, okay? So, okay, up to here. Everybody? Good. So now we will become lazier, less general, but it's still everything is still right, okay? So now let's try something very naive. Zero further, okay? So we are doing zero further, meaning we are wasting our effort. How about H prime is 0? It's not there. That means you have no H prime. that is zeroth order. You only have the H0 part, okay? But the nice thing is that you have 0 here, all the integrals are zeros, therefore you have the time evolution. I use zeroth order here, is 0, right? That means all the coefficients are time independent, they are just constant coefficients. That's nice. We know that it is the case because 0th order means we only have the solvable time independent part. All the coefficients there are time independent. It takes on a constant numbers given by the initial value. Okay, so at least we haven't done anything wrong by taking the 0th order. Okay, that is a good check. So understand? At least things are consistent. So let's get at the key answer. So for our discussion, the atom light interaction initial value problem, we are interested in a particular initial conditions. They are at time equals 0 or negative time before light comes in, the system is 100% in system number 1, state number 1, sorry. And then, therefore, it's definitely not in state number 2. That is the initial problem, okay? And if we ignore H prime, 0th order, we know that the answer is the 0th order coefficient will remain 1 and 0 all the time. That is to say, you ignore H prime, no transition. Makes sense, at least. But that also motivates us to write down the answer for first order approximation. Now, for those who want the formal approach, read sample question 18. That is list, the procedure is described very detailed in that sample question, and the TA will work it out for you, but the answer is the same. I like handwriting things more than, mathematics. Mathematics is important and useful, but sometimes you already sense the result. Why bother? Okay. So here, let me just sense the result and get it out. Okay. So now we know the following situation. 0th order, we ignore H prime at all. These are constants. The atom will stay in state 1 forever and will not be found in state 2 forever. Now, we want to start with these two equations and get at what is the first order correction to the coefficients. My argument is as follows. You already see one factor of H prime in all this term. Therefore, if we plug in the 0th order coefficients here, this term are automatically first order in H prime, one factor in H prime. That will give me the first order time evolution. I mean the time evolution of the first order coefficient. Okay, so that is my sense. Okay, so that's what I wrote down here. Plug in 0th order into the two equations, then you will get this thing, the time evolution of the first order coefficients. So let's do it, apply the idea. That is to say, I will plug A1 equal 1 and A2 equals 0 into the two equations. Okay, especially look at the first one. This is 1, so this term is there. This is 0, this term disappears. All right, So I have this thing. Okay, this is what I copy through. Okay, now I want to know A to T. The probability amplitude of finding the atom in state 2 at time t after the light comes in. Okay, so what to do? Bring the dt to this side, integrate over time from 0 to t, divide by 1 IH bar. Okay, so divide by 1 IH bar. Okay, bring the dt over, integrate from 0 to t. This is how you solve this differential equation, right? Okay, so we are done. Okay, this is the most important expression to move on. So far, it is good for any form of time-dependent perturbation, not restricted to our cosine omega t, that is called periodic perturbation. You may have flat bottom, time equals 0, boop. That's it. This is called sudden change in time. This works. Or time equals 0, boop. 1 second later, stop. That is also time dependent. Okay, this expression works. All right. Now, secondly, look at the ingredients. We have a spatial integral to do. Okay. And then we also have a time integral to do. And then at the end, we integrate over to a certain period of time. We get this as a function of time. And if we do this, then it is the probability of finding the atom in the upper state. Okay? So to be very explicit, let me use what we discussed today. This is the form of the perturbation. All right. We have the atom thing here. We have the light thing here. This is light atom interaction. Interesting thing. So let's plug it in. I mean, plug it into here. All right. So you have a mu that depends on the position of the electron that has to do with the spatial thing. You have a cosine omega t prime that has to do with the time thing. So both integrals have something to in. Okay, so here you have this that is responsible for this spatial integral. Then you will have a time integral to do. Okay, so if you single out the spatial integral with the time integral, you will find it is a product of two integrals. One is the spatial integral. Okay, so this is ER minus, okay? And then one is the time integral. Now, both are very interesting. Do you see that this is a exponential I omega t prime plus E minus I omega t prime over 2? Now, do you see that there are two terms? Energy difference of atom, okay, plus h bar omega, this minus h bar omega. So there are two conditions that this probability amplitude is not 0. Either it is absorption, E2 minus E1 is h bar omega, or it is emission, E1 minus E1 minus E2 is h bar omega. Okay, one is stimulated absorption, the other is stimulated emission. They come into one expression that is unavoidable. So stimulated emission is simple stuff in Schrödinger quantum mechanics. Okay, so let me see what is on the next part. Okay, so basically I'm done. Okay, now let me summarize in 30 seconds. This term, if it is 0, that means the transition cannot happen. It's called forbidden transition. If it's not 0, it is allowed. That will give us selection rule. That is to say, when is this integral is not 0, you will have this delta ML equals 0, delta ML equals plus minus 1, this kind of thing. Nice. That is the origin of the selection rules. This thing will give us the energy requirement. E1, E2, h bar omega. H bar omega must hit the difference. Otherwise, this integral will vanish. Then you have no probability finding it. How nice. Simple Schrödinger quantum mechanics give us a lot of real physics. Observable, they are observed in experiments. Okay, so I will stop here today. I will stay around. You have questions, please ask. Okay, and then we will continue on in extracting the physics out next time on Thursday. So long for now.